Okay, maybe we'll get started.
Yep.
So thanks for everyone. Thanks everyone for coming to the pre-event math session. So the motivation for this is that S curves appear in Adam's talk. Many of you will have seen S curves in the context of learning about logistic growth. Logistic growth is one of the most popular simple models of population growth. And because it's connected to what Adam's going to talk about and it's interesting, I'm just going to revisit this topic. So, logistic growth. So the simplest model of growth is the exponential model. So in the exponential model, maybe I'll start with that. So I'm writing on the blackboard. If you can't see that in your field of view, just walk over here and you should see it. So the simplest model of population growth is the exponential model, which just says that in any unit time, any individual in the population, usually you only count females. Tamer will approve of that. So you usually only count females, and then in any unit time you put in the model that there's some probability of any individual giving birth, which means that the more individuals there are, the more there will be in the next unit of time. And this leads to exponential growth. Now that's unrealistic because there are always limits to growth in practice, and so the next simplest model you can imagine is one that incorporates those limits to growth in the simplest possible way, and that's logistic growth. So I'll just derive, basically all I want to do before the talk is derive and explain what a differential equation is. So consider the following setup. So we've got a population, or it could be any quantity really. I mean, you could substitute the carrying capacity of the population with some other kind of limit to growth of whatever quantity it is that you're modeling. But let's say a population. So there's a population PT at time t. And the only way it varies is by births. Okay, you can incorporate deaths. That won't change the model very much, but for simplicity, let's say births. So of course the population is only going to increase, and the question is how fast is it increasing at any given time. Okay, so here's sort of the timeline. And we imagine that at some time pt0, there's a population pt0, and then at some later time t0 plus delta t, there's some population pt0 plus delta t, and so on. And we make the following hypotheses. So the first hypothesis is that the number of births that take place in any given unit of time is equal to some probability of giving birth so it's uniform across all individuals. So it's just some fixed probability of giving birth, and then you multiply that by the number of people, and that gives the number of births. And further, we're going to assume that that probability of giving birth is the same in every unit of time. So this probability is of the form b delta t for some b. So if you doubled the amount of time in between these measurements, you double the probability of giving birth. Okay, so there's some constant b. Okay, so that's the assumptions that go into the model. Now I'm going to switch over to the next board and turn that model into a differential equation. Okay, so if we just take that assumption, what it leads to is the following, that the population at the next increment of time is the original population plus this increment, the number of births, which was by hypothesis b delta t pt0. Now, here's the second hypothesis, which is to do with the fact that I said that there's some limit to growth. Okay, so this number b, well, I said it was constant, but I didn't really mean that. It would be constant in the exponential model of growth. But what we're going to consider is the fact, I mean, if there's a limit to growth, that means that the birth rate depends on the population. You might imagine that the higher the population, the lower the birth rate. Okay, so there's some kind of function that's decreasing, like something like that. How exactly? Well, the simplest thing you could imagine would be linear. That is, the birth rate decreases linearly from some maximum value, we'll call it B0, to 0, no new births. And let's say that happens at some value of the population C, we'll call C the carrying capacity. And if you have a straight line with y-intercept B0 and slope negative rise over run, which is B0 over C, then the equation of the line is given by this. Okay, so that means that I can continue this equation to write pt0 plus delta t as pt0 plus b0. Well, let's just factor out the b0, I guess. So it's b0 1 minus 1 on c times p. Okay. I kind of want to undo that line that was earlier. I can't do that, so let's just do this. Okay, so all I'm doing is substituting this in for b. Yeah, delta t, pt0. Okay, third board. Let me now, what I want to look at is the rate of change of population. So that's what I'm trying to compute. Oh.
Sorry, could you explain carrying capacity?
It will acquire the meaning carrying capacity in a moment when we look at solutions for the. But at the moment, it just is the place where that birth rate becomes 0, the population at which that happens.
Okay.
James, this third whiteboard isn't working for me. I'm not sure why, so I think I'll stick to this first two. Okay, so back to the second board. Sorry to jump around. So if I subtract pt0 from the right-hand side, that gives me the change in population over that unit of time. If I want to get the rate of change, I divide by the amount of time. And if you examine the first, the previous line, you'll see that that takes the form B0 1 minus 1 on C P P T0. Okay, so that's basically it. It says that the rate of change of population is equal to some quantity that depends on the population, but also the difference between the population and this number c, right? So there's a multiplicative factor here of this. Examine this factor. If p is very close to c, then p over c is very close to 1, so that term in brackets is very close to 0, and the other multiplicative factor is the population itself. So this is the rate of change of population. And now we just consider what happens when the amount of time becomes very short, and this is a differential equation. So I'm going to go back to the first board now. So the left-hand side, as delta t goes to 0, is the instantaneous rate of change of the population. That's written dp dt. And the right-hand side is as it was. Okay, so this is called the logistic differential equation. I've actually forgotten where the name logistic came from. If somebody remembers, they can comment. Okay, so I want to point out a few sort of salient features of this differential equation. So, I mean, the point of differential equations is, well, first you can try and solve them and actually find, to solve a differential equation, that's not how you spell solve. To solve a differential equation is to find a function, an explicit function p of t, which makes that true, that is, which gives the value of the population at any given time. You can do that in really baby problems like the ones we teach in first year calculus, but for any interesting differential equation you probably can't do this in any interesting generality. So what's more interesting about differential equations is the game of looking at the differential equation and figuring out what it says about the behavior of the system. So I want to go through a few obvious sort of features of this DE. First of all, so you should read it in the following way. If you know the population, you can figure out how the population is going to change. So if the population is less than the carrying capacity, then have a look at this term in brackets. If p is less than c, then p divided by c is less than 1, so that term in brackets is positive. The population is positive, so that whole right-hand side is a product of positive numbers, therefore positive, which means that dp dt is positive. And if the rate of change is positive, then the population is increasing. Okay, so that makes sense. If the population is less than this number c, it will increase. If p is greater than c, then that term in brackets is negative, so the population decreases. What else do I want to say? So as p approaches the carrying capacity, that term in brackets, remember p on c will be close to 1 if p is close to c, which means the term in brackets is getting very, very small. And p is getting closer to some fixed number, so that product on the right-hand side of the differential equation is becoming very, very small, which is to say dp dt is going to 0, which is to say that the population is growing slower and slower as p approaches c, either from above or below. And finally, if p is much less than c, examine the term in brackets again. If p is much less than c, p divided by c is very small and can be neglected. And that means that the differential equation for very small values of the population relative to the carrying capacity roughly looks like just B0P. Now that differential equation describes a population that in every unit of time increases by an amount proportional to the current population. That's exponential growth. Okay, so just examining the differential equation and doing some basic kind of reasoning, we've discovered, most of, maybe half of the interesting features of logistic growth, namely that for low populations there's exponential growth. The population keeps increasing until it reaches some carrying capacity where the growth slows down. And if you were to start the population above the carrying capacity, it would decrease, and again, until it slows down as it reaches the carrying capacity. Okay, so what I'm going to do is just sketch on the second board basically what solutions to this differential equation look like. So the x-axis will be time. The y-axis is population. Let's say this is the carrying capacity. And I'll draw a few different solutions in different colors. So let's consider a solution in green which starts with a low population. So that's a population less than C. Its initial growth will look like exponential growth, and then it tips over at some inflection point and approaches the carrying capacity. Whereas if it starts above the carrying capacity, it will just decrease to the carrying capacity. Okay, so for the purposes of challenge 3A, I want to highlight 4 regions in these solutions. Oh, I meant to draw that in a different color. It doesn't matter. Okay, so this is region 1. So here's initial growth for a solution which is less than the carrying capacity. This is region 2, sort of the tail end of that, where it's approaching the carrying capacity. This is region 3, which is the initial behavior of a solution above the carrying capacity. And this is region 4, the final sort of asymptotic behavior of such a solution. And I will ask you some questions about that later. Okay, but we have a few minutes before the main event. Are there any questions about logistic growth?
Dan, you mentioned somewhere a new perspective on the logistic differential equation. I'm wondering if you could just point out what do you think is interesting, particularly interesting about this perspective?
Yeah, maybe a new perspective is overselling it a bit, but challenge 3A will ask this question, so I won't spill that yet, but
cool.
Maybe should I even comment? Well, maybe I'll say that if you look at these 4 regions that I've identified, there's probably one you haven't thought sufficiently carefully about. And that's all I'll say for now. Any other questions?
Yeah, I've got a question.
Yep.
So I'm about to do the very unpopular thing, which is to arrive late and then ask questions about things that were done before I was here. But allow me to do so anyway. So this equation, dp dt is equal to b naught 1 minus 1 on cp times p. Does c depend on t, or is c just a constant?
C is a constant. I mean, you could make that depend on t, of course, but...
Right, so how do we understand this p is in between 0 and c, just for all t? Is that what that means?
Oh, yeah. Right, so this is something that's only properly you can only properly pass with the voiceover that was going with it. So
right.
if the population is currently at time t between 0 and c, then dp dt will be positive.
Oh yeah, that makes sense. All right, sorry. Yeah. Thanks.
Okay, so feel free to ask me more questions later, but for now let's move over to the slide display for the main event.